Okay, we're now recording, so let's go back to full screen on this and go back to the whiteboard. All right, now let me move my things around. You can't see these, but I have a big black taskbar that goes at the bottom, and it covers a large part of the whiteboard. And then there's a big black taskbar at the top that's for the whiteboard, and it blocks a lot of it. And when you were writing or somebody else was writing last time, because y'all can't see it, you were writing under it. I don't think you were. I think it was I have one other student in another class who also has a whiteboard, and she was doing it. And she was writing underneath the taskbars, and I couldn't see what she was writing, so I had to ask her to say it. So I'm trying to move those out of the way. Okay.
If you click the taskbar, you can move it.
What's that?
If you click the
Yeah.
taskbar, you can move it around.
Yeah, I did. That's what I was saying.
Okay.
That's what I was just doing, was moving them out of the way. And but I didn't realize it was, because I usually write around it. But then when she was writing, I went, oh, this is in the way. So I had to find a way to move it. Okay. So I don't think it'll take me too long, but this is for people who aren't here yet to know what we're talking about. Okay? Early in the morning, it doesn't work too well. dy dx, that's supposed to be a d there, by the way. dy dx is equal to, this is example 1, top of page, I've said this before, but I wasn't recording. Top of page 38, chapter 2, first order differential equations, 2.1, solution curves without a solution, okay? And here is your differential equation. dy dx is equal to 0.2. I'm not going to slash zeros because that takes more effort. 0.2 x times y. We've seen that one before, okay? But let's pretend we haven't, okay? But this was in figure 2.1. No, this is at the bottom of this page, okay, 2.1.3a, okay? But we did the problem earlier, okay? Now, on my old computer, I had a graph board, and I would have gone to that by now and already be working on it. I forgot, this new computer doesn't have a graph board. You don't know a way to get this whiteboard to become a graph, do you? I can't see any way to put a grid on it. I think I've looked and tried before, and I haven't managed to find that. But I'm a dinosaur, so I may have missed something. But let's just imagine we had a grid there, okay? Now, again, reviewing what we said last time, what does dy dx stand for? Now, this only works for first order differential equations that are written what they call in normal form, where you write the dy dx here and your function of xy here. That's exactly what we've got. What does dy dx stand for? Back in Cal 1?
Derivative?
Yeah, it's a derivative, and it represents the slope of a tangent line at any point, right? That's what change of y over change of x is, a slope. Delta y over delta x. That is a slope. Now, pick a point, any point. Now I'm going to do a really lousy job. I could do a better job if I go to a line draw, okay, of a graph board. Okay. And that's almost horizontal. Not quite, but close. So I think I'll erase this one. Now, for some reason, when I do much of this, after a while, I can't use the taskbar anymore, and I don't know why. Say the eraser won't change. If I'm in eraser, it stays in eraser. If I'm in text, it stays in text. If I'm in draw, it stays in draw. Right now, I'm able to swap around some, so there's a graph board. Now, let's tick off a few points here, and I guess I'll stay here. So let's do 1, 2, 3. It might be better to draw these. Okay. Maybe not. Okay. These are not pretending to be evenly spaced, but pretend they are. Okay. I don't need this many, but I'm putting them in here. I'll never get that far out. Okay. I miss my old graph board. I guess I could develop a new one, but I just never seem to have time to go back and catch up on things like that. Yesterday I thought I was catching up with stuff, and then here came a request from the administration to complete some sort of technology survey. I went, oh, you got to be kidding me, and this is like almost 10 o'clock at night. I said, no, I can't do it tonight. So I thought maybe I could do it in 30 minutes this morning before class. I couldn't get a good computer to log in well. So it's just always something. On my old one with the ionizing pen, I got so I could just click off these things so fast. And not badly spaced either, but that was old days. All right, pick a point, any point in the world, any XY point. Pick one. Anyone. Okay, I can't hear you. Okay, you're getting awfully faint. I don't know if it's my speaker.
Is that better?
Oh, that's much better. I don't know what happened there. I was just about to change mine. Pick a point, any point.
3, 2.
3, 2. Okay. When x equals 3, okay, well, we'll first find the point. There's 3 and there's 2. Would you agree that's about the right point? Something like that. Okay? At that point, plug in x equals 3. Y is equal to 2. 3 times 2 is 6. Times 0.2 would be 1.2. Whoa! Oh, Dawson's in the waiting room. Should we admit him? I don't know. I guess so. Okay. Dawson, you here yet? Maybe not. All right, good deal. Okay, we're on example 1, page 38, chapter 2, first order differential equations, and 2.1, solution curves without a solution, which sounds sort of crazy. So again, dealing only with first order differential equations. This equation, first order differential equation, is written in what they call, I think back in chapter 1, normal form, where you have dy dx on this side and your function of xy on this side. Okay? And I've drawn this really ugly graph, and Melissa chose a point 3, 2, which I put on the graph right there. You see the 3, 2. Very slight point there, but it's there. So what we're doing is plugging in x equals 3, y is equal to 2. 3 times 2 is 6, times 0.2 is 1.2. So at this point here, your slope is just a little bit greater than 1. Now, oh, wait. I can do better than that, I think. The draw has an arrow key. Okay. So let me first go back and erase that. Oh, I erased my 0.2. Okay. Maybe I can get it back. Okay, let's do an arrow key here. Would you agree that's about 3, 2, where do you see my crosshairs there?
Yes, sir.
Okay, is that about right? Okay, a slope of just over 1. Boy, this is sensitive. Would you say that's just a little bit greater than 1? One would be perfectly diagonal. This is just, I tried to get it a little bit north of that. Okay? Give me another point. Any point. Pick a point. Anybody?
5, 1.
5, 1. Okay? That would be 4, 5 here. Go up 1. So I better go back to just the pen here. 5, 1 would be something about here. Would you agree? Okay, there's your point. Okay? Now, plug in a 5. 5 for x, 1 for y. 5 times 1 is 5, times 0.2 is 1. So that one should be exactly on the diagonal. So it's almost parallel to that one, not quite. But I'm going to try to do it about like that. I don't know if I'm good or not. Give me another point. Any point. Anybody?
One, 1.
Second?
1, 1.
1, 1. Okay. 1, 1 will be right about here. Okay. I'm going to try to just draw the arrow. Let's plug in. X equal 1, y is equal to 1. 1 times 1 is 1 times 0.2 is right at 0.2. So that's just a little bit more than horizontal. I don't know if I can tilt it up just a little. Maybe that. Let's just imagine that's 0.2 slope. Is this making sense? Give me another point, any point.
1, 5.
1, 5, okay? Plug in a 1 for x, a 5 for y. That would be 5 times 0.2 would be 1 again. So 1, 5 you said, right? There's 1, 2, 3, 4, 5. Boy, I got those way too closely spaced, didn't I? Okay, let's just imagine that's the point, and your slope is 1 again. I'm hoping it's close to 1. All right, you get the general idea. We could go to the other side. Let's do something in quadrant 2 or 3 or 4, just not in quadrant 1.
Negative 3.
Negative what? 3?
Negative 3, 3.
Negative 3, 3. So the x negative 3, the y positive 3. Let's plug those in. Negative 3 times 3 would be negative 9 times 0.2 would be negative 1.8. So at negative 3, 3, which I think is right about there, what did I say? Negative 1.8, so that's almost a negative 2. So it's pretty steeply south, okay? Agreed? Give me another point. Anybody? Any quadrant?
Negative 2, negative 3.
Negative 2, negative 3. That multiplies to be a positive 6, doesn't it? Times 2 is positive 1.2. Negative 2, negative 3 would be somewhere right about there, and a positive 1.2, just a little bit more than the upper diagonal. Okay? You see what we're doing here? Let's get one in the fourth quadrant anyway. Anybody? Negative what?
6. Negative 6, 2.
Negative 6, 2. That's back in the second quadrant, but we can do it. There's
Oh,
1.
sorry. I meant 6, negative 2.
6, negative 2. Okay, 6 would be out here. I think that's 6. Yeah. And negative 2 would be down here. And let's do the math on it. 6 times negative 2 would be a negative 12. Times a 0.2 would be about a negative 1.2. Let's see if I can approximate that. Just a little bit. I probably did it too much. A little bit more than diagonal south. Okay? Now, if we pick... Okay, now I'm going to be really lazy here. Y'all are hardworking people, I can tell. I was going to choose 0, 0. What's the slope when you're 0, 0? 0. Okay, so I'm going to try to do a horizontal slope here. There, okay, did it. Okay, give me another coordinate point. something on an axis.
0, 2.
0, 2. That would be up here. What would it be? 0. Give me another coordinate point.
3, 0.
3, 0. That would be over here. What would its slope be? 0. Okay. I like zeros. Well, not on your test. Okay. Give me another one. How about on the negative x-axis?
0, negative 2.
Negative 2, 0?
0,
Okay.
negative 2.
Oh, 0, negative 2. That would be on the y-axis right here, right? What's its slope?
0.
0. Got it. Give me something on the negative x-axis.
Negative 3, 0.
Negative 3, 0. There's one right there. And what would its slope be?
0.
0. Whoops. That messed up. Let me see if I can correct it. There. Well, that's interesting. It disappeared. Let me try it again. There we go. All right. Now, you get the general idea. All up and down the y-axis, the slopes are 0. All right and left on the x-axis, the slopes are 0. Whoa, here comes Casey. Now, let me see. Casey. I don't see a Casey, okay? Is Casey in the room yet? Casey,
Still connecting.
Yeah, I see. I see now. I just pulled up my thing. No microphone, no nothing. So, as I was saying to Melissa when we were first logged on, they're still adding students. We lost Casey. And Casey could be either a male or female, so I don't want to say which until I hear from him or her. I don't know. I hope Casey will come back. Okay. Is this at all daunting to get onto it the first time? I take it y'all don't have any problems. But do you remember back when the first time you ever got on a Zoom?
I think it was stressful making sure you typed in the correct
Right.
password and link number.
Right. So you didn't just open your computer, click on it, and it popped up?
No, I clicked
You copy the...
join Zoom and then I just typed in
You typed in.
copy and
Okay.
paste thing.
Yeah. When I sent one, maybe because my wife told me I could do this, when I see the link there on whatever the invitation is, I just click on it and go, and it opens. Do you type it in every time this time?
I normally do because I don't think the link is a hyperlink,
Uh-huh.
so I don't think we can click on it, but I could be totally wrong
Okay.
and have been wasting 2
Well,
minutes of my life.
I don't
every
know
time.
that you are. It may just be that, here's Corbin coming in. I forgot to circle his name before. I forgot to circle yours too, Dawson. I was hoping you would just, no, I didn't say that. Okay. And Cole, I forgot to circle his because I knew y'all and didn't circle your names. Okay, so Corbin is not quite here yet, but he's getting close, I hope. I just don't know who Casey is or was, or if that was a mistake or someone was just trying to, what do you call, crash the class. I guess that's what it was. I always have that problem. People are always trying to get in to differential equations classes. Okay. But Corbin's not quite here yet. Can y'all tell he's still trying?
Yes.
Okay. I see his name, but no microphone, no camera, not even red with an arrow through it, just nothing there. And that's the same thing I saw with Casey. And that's why I was wondering, Dawson, did you have any trouble getting on this morning? Okay. I had trouble even getting anything in my system to work. I was telling Melissa I had to, first thing I did shortly after 8 o'clock, when the computer came on and stuff like this, I was going to upload the last night's class because it was still loading when I quit and went down to eat supper because the class got over with at 6:15, and then I set up the Zoom for today and all that kind of stuff, and had a few other things to do. Oh well, let's see. Corbin's got a microphone. Can you hear us yet, Corbin?
Yes, sir.
Good. Okay, welcome. There was a Casey trying to get in earlier. That wasn't you under a different name, was
I
it?
actually signed in the wrong account. I'm sorry. I signed in with like Google or something.
Okay, that was you?
Yeah, that was me. I was just on a different account. I was on the wrong account.
Okay, all right. So I was thinking they may have added someone else to the class this late in the game, but it's been done before, and I think it's going to be done again. I had an email last night that was, I just found out I need another course to get financial aid. Can you add me to your course? I said, well, this was not to this course. It's linear algebra. They also have already had the first test, finished the first chapter. I said, well, this is where we are. I'll take you in the course, but you've got to catch up. And I don't know if they've added them or not. All right. Well, anyway, Corbin, welcome to class. And where we are, I'm going to shut this down so it's not in the middle of my screen. Okay. We're on page 38, chapter 2, first order differential equations, section 2.1, solution curves without a solution. And what we were doing this, and this is a pretty ugly graph. I wish the whiteboard had a graph faculty to it, but it doesn't. And this, when you set up an equation like this, this is first order differential equation. Now this happens to be a linear first order equation, but that's not beside the point here. You set it up in what they call normal form, I think is the one they call this, where you set the derivative on this side and the function on this side. That derivative, f prime or y prime, whatever you want to call it, is equal to your f of xy over here. Okay, what does that set up for you? That tells you what the slope is at any point that you plug in the coordinates here. So we drew the graph. It's pretty ugly and ill-spaced and all that kind of stuff, but Dawson's used to that. And then we were picking points, any point on the coordinate plane, okay? And as you pick the point, we just put them in. This one was -3, 3. When you plug a -3 in for x, a +3 in for y, that gave you a -9 times 0.2 was -1.8, and I tried to draw an arrow here pointing in -1.8 direction. Here was 0, there was 0, everywhere on the x or y axis, where either x or y is 0, y or x is 0, then you're going to have a 0 slope. So those were easy. None of the students chose an easy one. I chose the easy one. Okay, the others, we chose some points in every quadrant. And you see, you do get a picture that looks something like, believe it or not, oh, I don't have my camera. I don't see, am I anywhere close to that figure in the text? Right, left, up, down? None of you can hear me, right? Sorry about that. This is, I know I'm doing a lot of griping, but this fairly new computer, much newer than one I was using for years, I would say close to a decade or more, an old Fujitsu, but it was a tablet PC, but its microphone, as far as I know, was not directional, okay? This one I have to be talking directly into it. If I turn my head, does that phase out? Yes, it does. This one I have to be facing. If I hold up the book for you to see, the microphone's same place the camera is, and the book will block the voice. So even though I'm trying to talk around it, it doesn't seem to work. So anyway, Was I anywhere close to showing that figure that kind of looks like this one? Okay, you tell me if it showed up in the thing.
You have to go move your book up a little bit. Yeah.
Okay, so you see the one on the whiteboard looks pretty close to this one, doesn't it? We didn't draw all the points in there. It was pretty tedious, but not too bad. And you see the curves then. Let me go to the draw. Now this will be ugly. This will be awful. I don't draw good curves. But the curves seem to do this kind of number. I'm just going to make a guess here. They come down here. And then you know it's horizontal here. Goes back up here. And that's the curve. Down here they do sort of the same thing. They come up, flatten out, and go back down. If we had drawn enough points, better than that, okay? And that results in the second figure. Tell me if I'm anywhere close there.
I think down a little.
Down a little?
Yes, keep going down.
Now this is the one with the green lines, right?
Yes.
Okay. Still down?
You can see it there.
Okay. So I have blue lines, they have green lines, I don't care. There we have solution curves, and we don't even know what a solution is. Okay? So that's why they call this section solution curves without a solution. Okay? Now, let's do another one. Any questions on that one? All right.
Yeah.
All right. So let's do another one. I wish I had a... Okay, start this over again. With straight lines. Try to do straight line. Well, they're going to be straight, guaranteed, but I want it vertical, and this is not necessarily going to be vertical, but pretty close to it. Not quite, but close. Then do a horizontal one here for the x-axis. Not going to be quite horizontal, but hopefully I can get relatively close. Not quite, but close. And now tick off a few points. I'm going to try to space them a little more widely spaced. There's one. There's one. There's one. There's one. There's one. There's one. There. 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 Ooh. Sometimes the finger drags. Okay? And let's do some up this way too. I feel like Bob, what's his name, with the painting class. Y'all don't know who I'm talking about.
Bob Ross?
Yes, okay. And just a little cloud in here, you know. Yes, you do know. Good. I'm nowhere like Bob Ross. Okay. But I talk while I'm doing. That's what I was meaning. He didn't have to use a computer. He used skill. Okay. I didn't know you were old enough to know Bob Ross. But he's been all over the internet ever since, hasn't he?
Everyone in my high school loved Bob Ross.
What's that again?
Everyone in my high school loved Bob Ross.
Oh, okay. Y'all were an eclectic crowd, weren't you? Okay. All right, so here is the graph. It says use the direction field to sketch your... Oh, wait. Here's Ricky. Let me get Ricky in. Okay. So Ricky's here. I'm hoping that they're through adding students just so I can get off the piece of paper and into a grade book. Okay, I'm a dinosaur. I like grade books. Okay. So use Ricky, if you can hear me yet, can you?
I can hear you.
Okay, we're on page 38, chapter 2, first order differential equations, and 2.1, solution curves without a solution. We just did one. We're doing example 2, the bottom part of page 38. Okay, it says use a direction field to sketch an approximate solution curve for the initial value problem dy dx. So here's your equation. Whoa. Now for some reason I have a box there. I didn't want a box, so let me get this. Okay, now I got a pen back. I think I'll write it down here. It seems like I'm a little left more white space here than I did on the other. So here's going to be our thing, dy dx. This is interesting. There's a whole ugly y. Here's a dy dx. Okay, dy dx is equal to, pretty simple formula, it's just hard to write, sine x. I would type this in, except it doesn't let me do dy dx as I want to. I have to do a slash there, and that doesn't look like a dy dx. Now there's your differential equation. We have an initial value, and in this case it truly is an initial value. When x is equal to 0, which to me is a nice initial value, your y is equal to -3/2. Okay. Now, I should have done this first before I drew my graph, because then I would have drawn my graph differently. Well, maybe not. Okay? So, again, Ricky and Corbin both, when you write it in this form, a differential equation in this form, I think in chapter 1 they called this a normal form. You put the dy dx on this side. Sorry about that. Get out of there. Okay, dy dx here, and your function of x and y here. This one just happens to be a function of x alone. No y. You could have had a y in there, but we don't. First order. Now this happens not to be a linear differential equation. Well, wait, yes it is. Because there's no y in here, it's perfectly fine for this the function of x to be nonlinear. It's just the y's can't be nonlinear. So this happens to be linear as well. First order differential equation. Okay? Now, again, I would say, give me an xy pair. Okay? So give me any xy pair. Anybody?
1,
1, 1. Okay. Now, are you in radians? Yeah, let's say we're in radians. So I want the x in something like pi halves or something like that, because I prefer those. Maybe pi, pick one that's really easy to do. Pi 6. Say again?
Pi.
5 pi? Okay, let's just imagine these horizontal marks now are not 1, 2, 3, 4, but they're, let's call them pi's. So 5 pi would be out.
Oh.
Yeah.
I was saying like x is pi and y would be pi. So pi.
Oh, pi. I thought you were just hungry. No, I'm sorry. Nothing like that. Okay. Let's let the y-axis still be numbers. We don't have to be scaled. I'm not scaled. Obviously, my spacing is not scaled. So let the y-axis be numbers. Okay? So if you have x equal pi, which pi you said, okay? So that'll be right here. It doesn't matter what the y is. What is the x? What's the slope? What is sine of pi? Anybody?
1.
No. Sine of pi halves is 1. Sine of pi is? 0. Okay. Well, guess what, team? At all of the n pi's, your slope is 0. Okay? So I'm going to put them in here. because these are our pi. Ooh, that one twisted a little bit, but you'll just forgive that one. Okay, that one twisted a little the other way. That one twisted too much. I don't need to be doing these quite as fast. Okay. So all along here, all the pi's, they are exactly 0, including 0 pi. Okay? Okay? I'll just do a few in the negative direction. I don't know why it's pointing downward. There, something like that. Okay? But guess what? At any value of pi, the slope is 0, right? So you said pi, I'm assuming you modified that to be pi 1, because I did one of these. So you see, at anywhere where x is equal to pi, or 2 pi, or 3 pi, or 4 pi, you always are going to have a horizontal slope, right? Down here as well, because there's no y dependence here at all. It's all depending on x. So this is going to be horizontal, if I can make it horizontal. Get on up there. Slow down. Right there. So, oh, that's bad. That's supposed to be horizontal. Okay? That's horizontal. No. What are you doing? Some of them go right in place and some don't. So everywhere there, at all the pi's, your slope is 0. Negative pi's, positive pi's, all your n pi's, the slope is 0. At all your pi halves, the slope is what? You said it before, or I said it. 1. So all up and down here, the slope is exactly 1. All up and down here, it's negative 1. Okay, at 3 halves pi, it's negative 1. So I'll draw this one here. 3 halves pi, it's negative 1, like there. Okay, so all the half pi's, it's either plus or minus 1. Okay, here it would be, you can pick it anywhere you want to. I'll pick right here. There's a negative 1 again there. Okay, positive 1 here. Okay, so, okay, this is a pretty lousy rendition. Okay, but all up and down at all the pi's, and here these will all be positive 1s here. And I'm putting them on the grid lines, but they don't have to be on the grid line. Okay, that's supposed to be a 1. All up and down, above and below, they're always the same. This one would be a negative 1. Even if we're not on the grid line, that's going to be a negative 1. Ooh, one of those is wrong. I don't know which one it is. Okay, so you get the general idea here. Okay, now, not drawn very well, but still drawn. Okay, so everywhere in here, it's alternating up and down, up and down, up and down. That's sort of unfortunate here. But down here, everywhere along here is halfway down. Have I written the problem right? No, goodness gracious, nobody caught that. I was saying this is not.
Sine y?
Say again? Yes, that's exactly it. I wrote down an X and it's a Y. Okay, sorry about that. I was going to say this is nowhere close. I almost want to start over, but what I'm going to do, rather than start over, I'm just going to erase my arrows. I'm going to try to erase my arrows. Also arrows, as well as arrows. Okay, sorry about that. That's a sine y, not sine x, I was going to say. So this is not a linear differential equation. There, you let me say it wrong all the way along. I'm afraid to do on the grid line that it's actually going to lose it. Okay, so ignore those on the grid lines. Okay, this is a sine y. I was going to say this is nothing like what the problem is. Sine y. All right, let's start over. Now, let the y's be pi, 2 pi, 3 pi, 4 pi, 5 pi. In fact, let's do the y's as half pi's. This will be pi halves pi, 3 halves pi, 2 pi. Okay with that? And this will be negative pi halves, negative pi, negative 2 pi, negative 3 halves pi, negative 2 pi, negative 5 halves pi. Okay? The horizontal axis will let stay numbers. So, let's start over again. If this is sine y, at the half pi's, the slope, okay, first, all of your, when y is equal to 0, these are all 0 slopes here. So this one, let's see if I can catch it again. Maybe I have to go back to arrow. Okay, that should be a 0 slope. Wait, I'm doing it wrong. Okay. When y is equal to 0, yeah, your slope is always 0. So this should be a 0 slope. Everywhere a 0 slope. I'm not going to put them on the half. All these are 0 slopes. That's a 0 slope. Okay, I can't get up to erase. All those are 0 slopes there because when y is 0, your derivative is 0. Okay. Now, when y is pi, which is here, remember, you have 0 slope again. Everywhere that y is pi is a 0 slope. Doesn't have to be on the tick marks. It can be anywhere. These are all 0 slopes. I'm getting actually a little better at this. Oops, as soon as I say it, it screws up. Oh, worse. Okay. Brag. Okay. Anywhere here where y is equal to pi or negative pi or negative 2 pi or any multiple of pi, these are all zeros. 0 slopes. Agreed? Don't let me do something else wrong, okay? Well, that one didn't quite go in the right direction. Okay, your pi's, you're all horizontal slopes, okay? At your half pi's, here, let's start with positive half pi. Here the slope is +1. Here the slope is -1. Here the slope is +1. And here the slope is -1. Here the slope is +1. And guess what? All across here, the slopes are always +1 here, +1 there, +1 here, -1 here, -1 here, -1, let's see, +1 here. Okay? Everywhere where you're on a half pi, you're either a plus or a -1. Okay? Now, so the slope is 0s here, and then slightly increasing until you get to +1 here, and then they level off to go back to 0. Up here, they're 0 here, but now decreasing till it's -1, and then increasing to it's approaching 0 again. So your curves are all along there. Let's now go to y when x equals 0 is -3/2. Okay? There's something wrong with that picture too. Okay? When x is equal to 0, your y is -3/2. Okay. Well, up here you're going from 0 to -1. And this is a rather bizarre situation here. That is -3/2 radians, because your y is measured in radians here, okay? Or the way I've drawn it. No, it's not in radians, but it's -3/2. Well, I'm sorry. I'm making it far more difficult than what it really is, okay? When x is 0, y is -3/2, so you're down here. Wait, this is, okay. -3/2, I've drawn my graph in this, okay? This is -pi, right? That's how we drew it. -pi is -3.14, right? So pi halves is going to be almost, in fact, it's a little beyond minus -3/2, because one, okay, if pi is 3.14, half of that is 3/2, a little bit greater than 3/2, okay? So your 3/2 is here, and at this point, you're just a little bit, the slope is not quite -1, but close to it. But that's where this curve has to go. It has to go through here. So this curve, now this is going to be a terrible rendition of it. Okay, it's going to be coming, this is wrong. Okay, I forgot I was in, okay, need to go back to draw mode. Okay, here you're parallel to the, not quite, but close. You're hugging the x-axis here, until you come down here, and here you're going to start going back toward this horizontal asymptote. There's the curve that you're on, okay? It has to pass through the point 0, 3/2, or -3/2. -3/2 is almost -pi/2. Yeah, almost -pi/2, so it's just short of there, and that's where that curve goes. And tell me if I'm anywhere close. Do you see that graph? Right, left, up, or down? You probably can't hear me. Right, left, up, or down?
Where it should be.
Say again?
It's right.
Oh, amazing. Okay, I got something right today. Mark it on your calendar. Okay, so there is an example of an initial value problem. You have your direction field here, and of course I put all the marks up here when I should have looked at where my initial value was. It was down here. I should have done all the marking in here rather than up there. But that is how the pattern of your direction field went. Okay? Now, they do mention, going back in history, the method of isoclines. What that technically means, have any of you ever, this is a really strange question, do any of you even know what orienteering is? Yes or no?
Does that have to do with sailing?
Say again? You do it in sailing?
Is that a sailing term?
I'm not sure that it can't be used in sailing. All I've ever known it was in running, but I see no reason you couldn't do orienteering in sailing as well. Except sailing, you wouldn't use what I'm going to use as a description. So let's get back to running, okay? You are given a topographic map. A topographic map is one that has the isoclines, the lines of equal elevation, okay? So Stone Mountains, that's a ridge of mountains. Those are going to have lines that are very close together in the steep parts and flattening out further apart in the flatter parts, okay? That is called a topographic map. And that's what an isocline is. Iso means same, cline means is from the same derivation is elevation, I think. I don't know Greek or however it came about. But it's just like in a weather map. They show lines of equal barometric pressure. Those are called isobars. Okay? In a thermal representation, you would call them isotherms, connecting points of equal temperature. If you had oh goodness, there are any others you could use. But anyway, that's what they're talking about here, that they used to draw these kind of things before they had computers and stuff. They had the method of isoclines where they plotted on a map areas of equal elevation and then connected the dots. Okay? So anyway, that finishes. I don't know why they stuck that in here, but they did. Let's move on to 2.1.2. Autonomous first order differential equations. Now, what in the world do we mean by autonomous? Now, let me ask this question. Do all of you have books? I assume there's still 4 of you there. Am I right? Yeah, 5 in the class. I'm one of them. Okay. So I know Melissa said she had one. I believe, Dawson, you have one, don't you?
Yep.
Okay. Corbin, Ricky, you have the ebook or the PDF version?
I have a PDF.
You do have a PDF, so you can see what we're talking about. How about you, Corbin? Do you have a book or something that resembles a book? Corbin, are you there? Okay, maybe his microphone's not working. I'm going to assume you've got it so I don't have to type this stuff out. What do we mean by autonomous? Here's how they say it. An ordinary differential equation in which the independent variable, in this case that would be the x, quite often it is, quite often it's t, but it doesn't have to be either one of those. The independent variable does not appear explicitly is said to be autonomous. This is an autonomous differential equation. The x doesn't show up anywhere except in the dy dx, and that's just part of an operator there. It doesn't show up in the function anywhere. That's an autonomous differential equation. We just plotted an autonomous differential equation. The first one we did was not. 0.2 xy, not autonomous. This one's autonomous. Okay? So they give a couple of other, okay, in other words, the dy dx taken from here, let's just, to keep from having to write anything, just imagine that was there. This is just some function of y and y alone. No x dependence of your function here. Generally, this would be f of xy. Now, an autonomous is going to be a function of your dependent variable alone. Here's some examples of those. And this has nothing to do with the graph, but I'm just not going to do. dy dx is equal to 1 plus y squared. Depends on y alone, not on x. Now, by the way, this one's not linear because the y is squared. This one's not linear because it's sine y, okay? So this has nothing to do with linearity. It could be linear, but this is not. The second example is the one we did earlier. Dy dx is equal to 0.2 times xy. Not autonomous because it does have x dependence, okay? Now, if you think back at the end of chapter 1.3, when we looked at several of those applications of differential equations, when you had something like dA dt, this was probably the radioactive decay or rise or something, dA dt is equal to k times a. Okay? That's autonomous. The t is nowhere in the right-hand side. When we talked about those that dealt with disease spread, dx dt is kx times n plus 1 minus x. X there is your dependent variable. T is your independent variable. That would be autonomous. When we looked at the one with Newton's law of cooling and warming, d capital T by d little t, where capital T is temperature, little t is time, is equal to K times capital T minus capital T M, which stood for medium temperature, which means the temperature of the medium, not average temperature and stuff like that. I like to call it ambient temperature because that's how I learned it, okay? Again, the time is not involved, only the temperature. That's autonomous. When we did the mixture problem, where we had dA dt is equal to 6 minus 1 over 100A. The only variable on the right-hand side is your A, which is the dependent variable, not the independent variable. That's autonomous, okay? The other things in there, the T sub M, the K's, the those kind of things, those are all constants, so they don't enter the picture at all, okay? There was an N in one, that was that. Now, with an autonomous differential equation, like we've just been describing, the zeros of the function, f, okay, are of special importance, and we say that a real number c is a critical point of the autonomous differential equation if it is a zero of f. In other words, f of c is equal to 0. Now, not quite what we were calling critical. Well, it is. It actually is the same thing we were calling critical points back in Cal 1, okay? Because think of this. Here is your derivative. Your f is what the derivative is. F of y dy dx is equal to f of y. So your f is your derivative of y. Well, where your derivative was equal to 0, that's what we considered a critical point. Now, we also considered when they were not defined, we're not doing that. Sorry, we're not doing that here because we're only dealing with the zeros. But those were critical points before. They are still, sorry. Let me get something to drink. I don't know why my throat just clogged up. And by the way, that's just water, by the way. So if I get loopy, it's not. Never mind. Okay, these are critical points. Well, let's take a look at here. Where are your critical points here? Remember we said this was the autonomous differential equation? Where your f of y is 0. In other words, where the slope is 0. That's on the x-axis when y is equal to pi, 2 pi, 3 pi, I'm doing negative pi, negative 2 pi, negative 3 pi, positive 2 pi, positive 3 pi. Those are your critical points. The places where your f of y is equal to 0, or f of c is equal to 0, for whatever value you put in for the c. The c's would be, now here's the part that's a little bizarre here. Before, it was when the value c that we're calling critical was when the slope was 0, okay? But we were calling c the x value. Now we're calling c the y value, okay? Or the value of the dependent variable, okay? And those are called critical points. Another name for it is an equilibrium point or a stationary point. So in other words, if an object is here, it stays there. It's not changing any. Slightly below there, it starts curving, okay? But on this line, it never moves. It stays on the line. That's why you call it a stationary point or an equilibrium point. It's perfectly happy where it is. Up here, it's slowly going down till it reaches a slope of -1 here, and then it decreases and approaches that stable point again. But they don't ever touch it. Mine looked like it did, but it wasn't supposed to. Down here is a horizontal asymptote, and here, and here, and here, and here. And in between, you have curves that come approaching that horizontal asymptote up here, curving down and approaching it again down here. This alternate part, they're approaching the horizontal asymptote and then start sloping up gradually till we get a slope of a positive 1, and then they approach it again. But never do they cross, okay? Never do they touch. They just come close. The critical points here, the C's are in the dependent variable, not in your independent variable. We still call them C's, but now those are the Y values or the dependent variable. That's a little bit of a difference. That constant solution, y of x equals c, is called an equilibrium solution, and equilibria are the only constant solutions of that autonomous equation. Okay? So let's do example 3. All right. They're going to start this a little simpler than what we were doing before. They were going to do a lot of the same type things here. Here's your differential equation. So I'll go back to the top to write it. And this is going to be pretty ugly, as usual. dp, now this almost sounds like a population problem. And I don't know that it is or not. I haven't read to see. dp dt, it sure sounds like how something named p, could be a population or something else like that, is changing with time, okay, is equal to your original amount, p, I say original amount, your variable, independent variable p, times a minus b p. Okay, now that's not quite the same as the others we looked at, and certainly wasn't Malthus's population problem. So whatever this stands for, it's there. Now, what you have here, the a and b are just constants. The p is your dependent variable, t is your independent variable. The a and b are not variables, they're just constants. Okay? Now, they were very kind to you here that they wrote this equation as if it was they've already basically factored it for you. They could have written this equation little ap minus bp squared. That would have been a good way to write it, but they were very nice to you and wrote it as in a factored form here. Okay. Now, the reason I say that, if we do a little bit of analysis of this, we see, okay, what are we interested in? We're interested in where this slope is 0. In other words, this function is 0. And that's why factoring it helps it for you. To determine your critical values, okay, now the critical values aren't the t values now, they're the p values, where these are, the critical values are when this function is equal to 0, which is where your slope is equal to 0. Okay, well, when would that be? That would be when p is equal to 0. Obviously, right? That would make that true. The other is when this thing is equal to 0. And to keep from having to write it down, let's just do the math first. When a minus bp is equal to 0, we could add bp to both sides and have a is equal to bp, right? Let's flip them around and say bp is equal to a. So then p, that's what we're solving for, would be equal to, if bp is equal to a, then p would be equal to a over b. So guess what? We've just found our two critical values. Okay? Now, if we were plotting this, okay? Now remember your dependent variable is on the vertical axis. So let me get my line back here so I can draw a decent vertical axis here. It's on the vertical axis. Let's just pretend that's vertical. It's not quite, but it's reasonably close. Okay? Well, obviously, where x equals 0, let's just name that to be right here, that is a critical value. And then up here, x is equal to a over b. Okay, now I have no idea whether a or b are positive or negative. Let's just assume right now they're both positive, just for sake of this. They could both be negative and it'd still be up there, but if one was negative and one was positive, then it would need to be down here. So just for now, let's just assume both of them are either positive or negative. So a over b is that. Now that's supposed to be a horizontal line. Now the question here is, let me see if I can pull this line back up. Okay, because I want to extend this up just a little bit. Okay, poor planning here. Okay, now I think I'll go to, yeah, let me go. Okay, I'll use my arrow in just a minute. Okay, now here, and maybe I don't, okay, let me go back to my line here. The book's not doing this, but I'm going to do it, okay? Remember here, when p is equal to 0, your slope is 0, so guess what? This line that goes through here, the slope is always 0, because this, remember, is the p-axis. This is your p-axis here. Let me go back to draw so I can write it down, just to remind you. This is your p-axis here. Oh, why did I do that? Let me erase that. Okay, this is your p-axis. Okay, lift my finger. Okay, that's the p-axis. Here, p is equal to 0. That is a critical value. The slope is 0. Up here at a over b, I need to write that in here, but it's going to be somewhat in the way. This is the point a over b, and we're just assuming that's a positive value here. So let's just keep that assumption there. And we'll try to draw a horizontal line in here too. Oops, I didn't start too well. Okay. Let's just sort of say that's a horizontal line too. No, it doesn't look like it. Now the book didn't do this. I'm doing it. Okay, but that's another critical value, meaning your slope is 0 all along that line. That's what this equation says. dp dt, where this is your t-axis here, that is 0. So let me go and write in, since I've started writing. Let's do this as the origin. This is when p is equal to 0. So that is the origin, but it's also your horizontal asymptote here. Okay. Now, the question is, what is the function doing in between? Okay. Now, when a is greater than bp, this is going to be a positive number. Okay. When a is less than bp, this is going to be a negative value. We assume that a over b is going to be positive, so let's just say when p is negative, that's what down here is representing when p is negative, it really doesn't matter. Let's see, does it? Let's just assume this one's positive, then this is always going to be negative here. So your slope here, let me go back, this is where I wanted my arrow. So here is where your slope is negative, okay? Now, when you're up here, P is positive, and let's say that A over BP is also positive, then this will be this way. But up here, let's just assume, since we said here that's positive, up here then P is still positive, A minus BP now must be negative, okay? So that's how they draw the arrows in here. And obviously they had some assumptions here. Um, and they spell them out here. And anyway, this tells you. If your assumptions were different and the A minus BP was reversed from what we said, then just this one will go down and that one will go up. So whatever, but this is the example they gave. Now, they didn't show the lines there, but I want to put them in because that represents where this, so other words, now this doesn't mean it's going straight down, just does mean it's a negative value. The slope is downhill. Here the slope is uphill, here the slope is downhill. Reason it's downhill here is because P is negative here, and we're assuming that A minus BP is positive. Here it's going to be 0, and here, one side or the other is positive, the other side negative. Okay? They just arbitrarily chose this one. Now what does that tell you? That tells you this is a horizontal slope here, and it's always increasing, and then reaches another horizontal slope. So we have something a lot like our sine curve was before. Here, anywhere up there, it's negative, and it's coming down and is approaching the horizontal here. Here, it has to be a negative slope, so it has to be coming from close to that horizontal axis, and then it's getting more and more and more and more negative. It's never, there's no other critical value down here or up there, so they have fixed positions they can go. Okay? Now, that's what example 3 is. Now, I've read this several times, and I never do see why I guess they just arbitrarily choose that P is less than, let's see, you've got 3 intervals here, from negative infinity to 0, from 0 to A over B, and then from A over B to positive infinity. Okay? So, and these, remember, is your p-axis. So when P is negative, then this says, right off the top, that has to be going downhill. Now, that's the way they've set up their problem. When P is between 0 and A over B, which is the second thing they say, they're, without giving any details on it, they just tell you that's going to be positive in there. The slope is going to be positive. And when it's up here, it's going to be negative again. Now, don't think it has to alternate every time you cross one. It depends on the details of your problem. They're just telling you that's what this one is. Now, what they call this, without these horizontal lines in here, they call this a one-dimensional phase portrait, or simply a phase portrait of this problem. In other words, it just shows you on the p-axis where your zeros are, critical values. Okay, I like to go and draw that line in here just to remind myself the slope has to be 0 there. And then the slope can't change down here, because if it did, the slope somewhere down here would have to be 0 again. So if it started off being negative here, it's negative throughout. If it started off being negative here, it'd be negative throughout. They just told us in this problem it's positive in this range. In this one here, if it started out positive, then it would be positive throughout, but they tell us it was negative, so it's negative everywhere above A over B, because you can't have a direction change without having a slope of 0 again. That from your calculus 1 again. So anyway, these form your various solution curves. Okay? Now, they go into a bit more detail on these solution curves, and they draw some pictures here, and I really don't care for some of their pictures. Okay? I'll tell you why, the one I don't care for. Can you see the one that my finger is next to here?
Yes.
Okay. That one, the lower part of it seems to be approaching your horizontal asymptote. The upper one looks like it's going to collide with it. It can't. It has to be approaching it. So I don't like the way they drew that one in there. If that is indeed a critical value, which they indicate it is, C2, then that line had better start curving and approaching that horizontal asymptote. Okay? The lower part of it looks like it could be approaching that one. The upper part doesn't look like it is. Okay? So what a solution curve, yes.
Should it look more like this? I'm drawing it on the whiteboard. Like that?
That's how I think it should look. Because and if it did make a sharp turn there, that would be okay. But the way their picture looks like, it looks like it's continuing to going uphill, and that would violate the fact that it can't cross the 0, or it wouldn't be a 0 at that value. So you're absolutely right. So I think, and the next example is going to show that. But that's what we mean by a solution curve. If they just happen to tell you, here's a point right here. Let me go back here, go to our example. If they told you, bing, there's a point, let's call it our initial value, then you're not going to worry anything here, because that curve's never going to get down in this region. It'll never get up here in this region. But in this region, it's going to be sort of like you did, but in reverse. It's going to be doing something here that goes through there and then levels out there. Okay? Mine's obviously not very level, but you get the idea. Once you know a value, then you throw out the other two, because it can't possibly ever be in that other region. That's sort of what they're talking about. Autonomous differential equation. Once you know, you identify those critical values wherever they are, however they are arranged there, and I like to go on and draw in my horizontal things there. And then if you have an initial point, and that's what they were calling their x0, y0 in these figures, okay? If you have that initial point, you know it has the pass-through, then if it's on a curve with no restriction, yeah, it can look like that. But if it has a restriction there, it better curve and not cross or touch that critical value, okay? That was the only thing I had a problem there. Now, they talk for quite a bit here on that, and maybe it is valuable to go through. Read it, is what I'll say. I'm about ready to go on to example 4, which is going back and revisiting example 3, which unfortunately I've already, no, I actually have it up there. So I actually have one of the curves in, but sorry about this, but we have about 50 minutes or so to go. I need a bladder break. Do you have any objection?
No.
Okay, so let me turn off the recorder. So that's first class every morning. It's tough to make it all the way through. Fall and spring terms, when they last an hour, 15 minutes, yeah, I can swing that. But boy, these summer term classes, 2 hours and 15 minutes, nah, I usually don't make it on my first class. Subsequent classes most of the time, yeah, but not the first one. All right, so we're ready to move. Any questions so far? All right, so example 4 is going back and revisiting example 3. Now this is on page 41. This is, again, chapter 2, first order differential equations, 2.1, solution curves without a solution. Okay, which is a strange title, I think. So here we have example 4. The 3 intervals determined on the p-axis that we did up here, or you can also call that the phase line, by the critical points 0 and a over b, now correspond to the, in the TP plane. He's not used to calling it that. Used to call it XY plane. But remember, your independent variable was t, So this horizontal axis is the t-axis, and the vertical axis is the p-axis. So this is now the TP plane, little t, capital P, okay? It sounds like an Indian dwelling, but it's not, okay? Now, they correspond in the TP plane to 3 subregions defined by, and they give the titles to it. Let's see, yeah, I think I'm on this. They call this region 1. That's anything less than, P is less than 0. Region 2 is anything between, P is between 0 and, now let's see, am I numbering the same way? No, yeah, I am, okay. And then P3, region 3, unfortunately I didn't leave enough room for it. I regret that, but it's up here. It almost crossed the horizontal asymptote. Now their horizontal asymptotes are dotted lines. I didn't quite see how to do a dotted line. Let's see if they give us an option. I don't think they do. Maybe there's a way to do it, but I'm not about to try now. Okay, so there are your 3 regions. Region 1, less than P, less than 0. Region 2, between P equals 0 and P equals A over B. And region 3, when anytime P is greater than A over B. Now, and these are good for all real number t's, okay? Negative infinity to positive infinity. No restrictions there, okay? Now, and the phase portrait that we drew in, and they gave them to us, it says up here, the slope is always negative, 0 here, positive here, and 0 here, and negative all down here, okay? So you can almost, if you knew any particular points, and what they're calling those points, P0 being an initial value. Now the way I drew this one, this is not the way the book did, because I drew it here, I'm going to say that point right there is a P0, okay? P sub 0, okay? That's your initial point. When t is equal to 0, there's your p-value, okay? If your initial point when t is equal to 0 was up here, if that's your p0, now they're using the same p0, obviously it's only one of these, it can't be more than one of them, then this curve, whatever it's doing here, it's coming down and approaching this in this direction because the slope has to be negative. Now, if you had a P0s down here somewhere, let's just pick it here. When t is equal to 0, your P is that value, a negative value. That puts you in region 1. That must mean up here you're coming from the horizontal asymptote and heading south, and continue heading south. You might lessen the slope, but guess what? You can't, there's no place it's going to approach 0. So you just assume it keeps going south, okay? So there is, if for those 3 P0s, initial points, those would have to be how your curve looks. It may not have that exact slope, but it would have to be something on that order, okay? This one's always going to be sort of it's kind of like an inverse tangent curve, if you remember what that looked like. It's doing that, approaching a horizontal asymptote here and here. This could be anything, perhaps like a exponential decay curve, decay curve. And this again is another exponential decay curve, or something like that. It doesn't have to be, but both of those, no, this one would be a negative exponential decay curve or something like that. So it just something that has to approach a horizontal asymptote at this end and goes whatever it's going to do here. This one doing whatever it's going to do up there, as long as it doesn't change direction. Can never change direction because that would have to have a 0 slope if it's a continuous curve. But here it's approaching a horizontal asymptote. This has to approach the horizontal asymptote on both ends. So these are examples of autonomous equations. They could look like this, or like that on this one. Now, flip the arrows around any way you want to, and you can make these go in this one. This one could be going up like this, but it's still got to pass through that point. Here it would be on the negative side, approaching the horizontal asymptote, and then going up indefinitely there. If this arrow were reversed, then it would be coming from the horizontal asymptote up here, going through your P0 here, and then approaching that horizontal asymptote. If this arrow were up rather than down, then your undetermined increase would be here, going through your P0 and continuing on up there. Okay? And there approaching your horizontal asymptote again. So it just depends on what your phase portrait tells you, which way those arrows are pointing. But the horizontal asymptotes, from either side, they've got to be approaching those horizontal asymptotes. Does that make sense?
Yes.
All right, good deal. Now, example 5 is going to be dealing with some solution curves for our autonomous differential equation. This one's different, so let's clear the screen here. Okay? Now, here's your differential equation. I'll do it here. dy dx, I'm sorry, I always say dy dx. Yeah, it is dy dx. Sorry about that. It really doesn't matter what you name that second variable there. Because guess what? It doesn't show up anywhere else except right there. So that could be d stickman, whatever, because this is an autonomous equation. Everything on this side is going to have to do with y's. And here's how it deals with y's. It's going to be y minus 1 squared. Okay. That's going to be your autonomous differential equation. Obviously not a linear equation in y, because y is squared there. Now, tell me what the critical values are. Where is this thing right here, dy dx, equal to 0? Anybody? What will make this?
Y is 1.
Y is equal to 1, the one and only one. So your critical value is y is equal to 1. Okay? Okay. You can call that your C too if you wanted to. The only thing I don't like about calling it C, I'm so used to Cal 1 where C would represent a value on the x-axis. This is one on the y-axis. So just hang on to that and remember. Okay? Now, let me do my lines again. And I'll just try my best to make it as close to vertical as possible. It's not going to be exact. But actually, it came out awfully close. And then this one will be as close as I can to horizontal. I don't need this much room. That's not as good, but it's in there. Okay. Now, let's just sort of arbitrarily choose a scale here. I'll try to do the same way the book does. I'll leave as line to y is equal to 1, y is equal to 2, y is equal to 3. Y is equal to negative 1, y is equal to negative 2, not very well spaced, are they? Y is equal to negative 3, something like that. We're not going to really use those that much, okay? Well, what is your critical value? Y is equal to 1, okay? So let me see if I can approximate. I wish I could make this dotted. I can't. Let me see. Maybe it would help if I change the color. That's the format. And let's make the line maybe a little. What color you want this line to be? Not white. Pick a color, not blue.
Green.
Say again?
Green.
Green. Light green? Okay. Whoops. I messed that up. I was going to go with a lighter line width. Okay. Now let's do this. Oh, that's still blue. Let's erase that one. Okay. Now let's go with a new one and let's see if that will turn out being green. Green, green, it's green, they say? Yes, look at that. I guessed right. Okay. Now, I don't think I quite have it going through 1. And I think what I need to do is move this down just, ooh, that's the wrong way, isn't it? Wow, I would have guessed this one was too hot, too low. Okay, let's just say that's y is equal to 1. Okay? Now, let's do what they call the phase portrait. What can you tell me about the slope up here? They don't color your arrows. They just have an arrow, so I'll leave it green. What's going to be your slope above 1? Y is equal to 1. What's the slope? Guess what?
0.
Always positive, because y minus 1 squared can't be negative, can it? So, slope up here is going to be positive. How about the slope down here? Anywhere below y is equal to 1.
Positive.
Positive again. You got it. So here is your phase, whatever they call that, portrait, phase portrait, okay? That's on the up and up, okay? Now, that's your problem. Autonomous differential equation, dy dx equals y minus 1 squared, possesses a single critical point at c, or y is equal to 1, I like to call it, okay? It says that from the phase portrait, which we've just drawn, we didn't count on them, we see it's increasing everywhere. When in the negative region, when y is from negative infinity to 1, or in the positive region, when y is from 1 to positive infinity. Okay? Now, here they give us an initial condition. For an initial condition with y at 0, when x equals 0, y is equal to y0, but this y0 is something less than 1. So that means your initial condition is in this region down here. When x is 0, your y is somewhere less than 1. Well, if that's the case, you don't even need to draw a curve up here, because it will not meet your initial condition, okay? So it's going to be a curve down here. Now, did they give you a value? And you know it's increasing down there, bounded above by 1. So whatever that value was, it's going to be down here. And I'm just going to draw, well, let me not until we get a little further, okay? All right, but it would be a curve here, coming up here and approaching there, because the slope has to be positive and approaching 0 here. Now, if your initial value had, when x equals 0, your y was somewhere greater than 1, then you're in this region. But still, slope has to be positive, so that means you come along near the horizontal asymptote here until you cross at whatever value that was, and you keep going up. So it's one of those two, but it can't be both. Only going to be one of them. Okay. Now, Now, this comes from somewhere, I'm not absolutely sure where. Now, y of x is equal to 1 over, so let me, I guess, go back to my blue here. Actually, I'm going back to black. We haven't used black. And I think I'll also go back to a regular line width, not so thing. So here they come up with something I haven't quite figured out why. Whoa, this is not, I forgot I was still in arrow mode. I made an arrow there, didn't I? Okay. Let's go to draw mode here. Okay. Now, y of x, and so far I haven't quite figured out where they get this, but don't worry about that yet. Maybe it was somewhere I didn't read it closely enough. Y of x is equal to, I'm pretty sure this is what they mean, 1 minus 1 over x plus c. Now here is another gripe of mine. And it's probably my fault, but in the previous page, they called that C. Now let's not call it C, because now they're going to use C to represent the arbitrary coefficient, arbitrary constant in the thing here. So this C is not your critical value. So don't get those confused. Sorry about that, okay? That is a one-parameter family of solutions for this differential equation, okay? Now they say go ahead, jump ahead to problem 4 and exercise set 2.2. Yeah, we've already done those, right? No, that's a section ahead of us here. But they're just telling us this is a one-parameter solution for that differential equation. Without telling you how we got it, they're just saying it is. We take their word for it. Now, I was kind of expecting them to say verify, okay? And if you did need to verify, yeah, you'd have to take a derivative of this, and I would have written this as -1 times, or minus, parentheses x plus c to the -1. Take a derivative of it, go through the practice of that, and when you did, I think you'd come up and see that sure enough, that is a solution. They didn't tell you to verify it here. Not a bad idea to do so, because I sometimes don't trust them. But we're going to take their word for it. That is a one-parameter family of solutions for that differential equation, and they say you can look ahead to the next section and see if it's true. A given initial condition determines the value for C. For the initial condition, say y of 0 is equal to -1. So let's say that's your initial condition. Y of 0 is equal to, what was it, -1? Yeah, -1. Thought it was, but I have a good memory, it's just short. Okay? Now, if that's your initial condition, where are you, Waldo? We know x equals 0, so you're somewhere on the x-axis. Where are you in the y-axis? Right there. X equals 0, y is equal to -1. You're right there, okay? Guess what? You don't care about anything up here. That will not meet your initial condition, okay? Now, but this is your equation. So what you do with this value in mind, x equals 0, y is equal to -1, plug that in here. So the y is a -1 is equal to 1 minus 1 over x is equal to 0, so here is your c. Okay? Now, we want to solve for c to find out the value for c. So I'm all in favor of moving the 1 over c to the left-hand side and moving this one to the right-hand side. So that's going to give me, are y'all okay with that? 1 over c is equal to 1 plus 1 is 2. Didn't know you'd be doing such high-level math today, did you? Okay. Everybody agree with that? What does that yield c to be? 1 over c is equal to 2. C must be
1/2.
1/2. Perfect. Reciprocate both sides, or 1 over 1/2 is 2. Okay. So here is your solution then. Y at any value for x, not just at that value, at any value for x is equal to 1 minus 1 over x plus 1/2. Pretty ugly writing, but still there. Okay. Now, what does that tell you? Anything particular?
It allows you to figure out any coordinate.
Yes, it certainly does. I would maybe modify that any ever so slightly. Okay? And here's what I mean by that. What can x never be? Now we have another issue.
1/2.
X can never be negative 1/2. So if I'm going to try to, I can do them. Okay. Let's see if I can pop in some points here. There's -1, -2, -3, -4. I don't need this many, I'm just drawing them. And over here we'd have x equal 1, x equal 2, x equal 3, x equal 4, x equal 5. We don't need that many. Okay. So we have x can never equal, as you said, -1/2. Now I'm getting so fancy here, I'm going to go to a color red. And the reason I choose red, that's what I usually use for vertical asymptotes, because that red tells me you can't ever touch or cross that vertical asymptote. So I'm going to try to make it vertical as well as I can, which is not very well. And then I'm going to take this in and extend it downward here and try to keep it as vertical as possible. So that's going to be my vertical asymptote. Okay? Now let's go back to black. Boy, I'm getting fancy here, right? Back to black. Now we know where this solution curve is. Here's your initial value. Oh, let me get into draw mode. Here's your initial value. And from this point, I don't know where it crosses the x-axis. We could figure that out if you wanted to. Set y equals 0. Let's do that. It's not that bad. So when y is equal to 0, we're finding the x-coordinate. This is equal to 1 minus 1 over x plus 2, or x plus 1/2. I don't know why I'm doing this, just to be a sadist to myself, masochist, whatever, okay? So that means that 1 is equal to 1 over x plus 1/2. Which I hope also means that x plus 1/2 is equal to 1, right? Just invert both of them. So x plus 1/2 ooh, that's an ugly 2, is equal to 1. So that means x is equal to 1/2, which looks like it makes sense, right? So your x intercept is going to be at 1/2. Okay, so this then I think is a curve that goes up through here and approaches your horizontal asymptote in this direction. Don't cross it. Don't get, that's ugly. I'm going to stop there before I get any worse. But also approaches the vertical asymptote here. Now, for this function here, just this function here, we could have also drawn, pick a different color. Any color. Say again?
Yellow?
Yellow. I was just going to say that might not be a bad one. And the reason I think it's not a bad one, so up here somewhere you have another curve that, ooh, that does something like this. Okay, it's not that wavy, but you have another curve that does this, that satisfies this equation. But it cannot possibly satisfy your initial condition. It cannot possibly be up in this region because your initial condition is here. So even though this is a solution to this equation, it's not a solution to your differential equation. The differential equation with this initial value limits you to be this ugly looking curve down here. That's supposed to be a nice, smooth, even curve. That's what you're limited to. Okay? Does that make sense?
Yes. Does
Okay.
that specific curve have a name?
I don't think so. Let's call it Judy. Okay? No, I'm just kidding. I don't think they have a specific name for it. They just say that's the solution curve that meets all these conditions. It does not, this one up here does not meet any of the conditions. It doesn't meet the condition of your C, okay? It doesn't meet the condition of your other C, okay? It doesn't meet any of them, okay? This is that one. I don't know that it has a name. Sorry, I didn't mean to be flippant about it. All right. Now, what I'm going to do now, sadly enough, is to erase a lot of what I just did. Any questions before I erase it?
So the reason we have that curve is because it's a solution, but it does not meet all of the qualifications.
You mean why I drew this curve?
The
yellow
yes.
one? Yeah, I just drew it to say that is a solution curve for this equation. This equation fits there as well as here. But it's not a solution for this differential equation, even though we said this is your solution, this is a solution for that differential equation. But remember, to be a solution for a differential equation and to be a solution of a, in this case it happens to be a rational equation, those are different solutions because this differential equation happens to have an initial value, and that initial value limits you to not any solution for this, but only to the solution for this that meets that initial condition. So I drew it just to say this equation here, if you were in what? Pre-calculus algebra, when you did rational expressions and they said graph this equation, you would graph both pieces of it. But now we're in differential equations where this is your differential equation and they just happen to tell you that's your solution. But once they give you this initial condition, that rules out anything up here. That means you have to be somewhere on this part of the curve, not on that part. This part is not part of your solution for your differential equation. It would have been the graph of this equation here, even though this is your equation for your differential solution, the thing with the C evaluated here, but your initial condition put it down here, which means it can't possibly be this part up here. So this is your solution curve.
Would the
Okay.
yellow curve be considered a singular solution?
A what?
Would the yellow curve be considered a singular solution, or no? Because
No,
it
it's
doesn't
not
have
a
to
solution
be-
at all to this initial condition. Now,
Got it.
yeah, that would not be a solution at all because it doesn't meet the initial condition. You have to do both. And I don't know if you remember back in chapter 1, it said not only do you say what the solution is, you give the interval. This solution is only good for negative 1/2 is less than x to positive infinity. This does not have a solution anywhere from negative 1/2 to the left. No solutions there. Only has solutions here. So the interval of solution is from negative 1/2, open parentheses, negative 1/2 to positive infinity. That's the only part of this that has a solution curve. This part up here cannot possibly be a solution for this differential equation with that initial condition. Okay? Good questions. Excellent questions. All right. Let's do the second part. Can I start erasing now? Yay or nay? I'll take that to be yes. Okay. All right. Now let's see. Let me not erase too much because I hate having to write anything. Okay. So I'm going to erase the yellow. I'm going to erase the negative 1. That means I'll erase the red line. The green line stays. That was part of our issue here. I think all this can be erased. I think all this can be erased. If I found out I'm doing too much, I'll kick myself. Now, I probably did erase too much there, but I'll erase this part of it here, which will also erase this. Now, I probably can't erase the points that I drew there because that would erase the whole board, but I mean the whole axes. So just ignore those two black points you see there. Okay. Now, maybe I don't need all this, but let me go back to, all right, go back to the problem that they've shown here. And let's say our initial condition now is y of 0 is equal to 2. That's going to be how we change things. I'll change my, okay, y of 0 is equal to 2. Just a simple little change there, but that changes everything. So y at 0, when x equals 0, y is now 2. There is the point on it. What does that mean for us? That means you can't be anywhere, you can't be found down here at all. Anywhere down here. Your curve is going to be something approaching this horizontal asymptote and going up somewhere from there. Okay? So this is a completely different problem because you have, that was the former, and what I'm going to do is put an X through there, so that's not valid, and this is not valid. So forget about those points, okay? So let's go back to what we did before. Let's plug in. When x equals 0, what is, we're going to calculate and see what the arbitrary constant is, okay? So the y is now going to be 2, so we put 2 in for y, is equal to, now you see this is still true, this y cannot equal 1. It cannot equal 1, ever. So really, what I really should be saying is here, I was saying y is equal 1 is your initial value, but this says, well, we'll leave it. Okay, Melissa, your question. Y is equal 1 is a solution. That's a singular solution to this differential equation. Y is equal to 1 always works, because then dy dx is 0 and y minus 1 is 0. So that's a singular solution. Y is equal to 1 is a singular solution. Do you see that? It's not part of this parametric solution. That is a singular solution. You were asking about one. I realize there's one right there on the board. Okay? You okay with that?
Yep.
Okay, then let's write this. 1 minus 1 over, I could have left all this in there, that would have still been this. Okay? So what that means is 1 over c is equal to, and if I move this to this side, this to this side, this I hope will be a negative 1, right? Correct? I'm doing several steps at once. So that implies that c is equal to negative 1. Okay? Now this is not your c that meant critical value. This is your c for your constant, which means now that the f of x, and that's why I regretted I erased this, your f of x, I'm sorry, they're calling this y of x. You could have called it anything you want to, but I hate making mistakes with this because it's so hard to correct them. Okay, so this is your y of x now is equal to 1 minus 1 over x minus 1. Agreed?
Yes.
Okay, because c is now a negative 1. So, what changes do we make in our graph? Say that again?
X can't equal 1.
Okay, yes, x cannot equal 1, so that's now going to become a vertical asymptote for me. So here, oh, I'm supposed to be in line mode, okay? So let's see if I can get a vertical asymptote drawn here. I hope that's close to vertical. It's not quite, but it's close. And let me extend the line on down here. Whoa, where did it go? There it went, okay. Okay, there's our vertical asymptote, there's our horizontal asymptote, and the point's got to be here. So that means, let's go back to black. Now, do we even bother with trying to find an x-intercept? No, we'll never get an x-intercept. It will never touch the x-axis because your point's here, horizontal asymptotes down here, vertical asymptotes here. You're going to be somewhere, ooh, we don't want to be in line mode. Okay, we want to be in draw mode. Okay, so your function has got to be approaching your, that's ugly, 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 in that direction and approaching the horizontal asymptote for large values of negative x. That's where you are, that's where you're stuck. Again, your slope is up, has to be up here, okay? And sure enough, this equation right here would have had a kind of a mirror image of that, but across this way. From that, you would have had another curve here, slope up, everything would have fit, except it can never go there, okay? It can never go there because your initial condition here would not be anywhere on this part of the curve. So I'm not going to bother drawing it. They did bother drawing it in the book, so I guess I will. You want to make that yellow again? This is not part of the solution, but I'm just copying what the book had. it would have gone up like this, not touching it, and down like this. And again, not touching it. That would have been part of your solution of this equation, but it's not a solution of your differential equation with that initial condition. Can't be. It's a solution of this rational equation that you would have done back in pre-calculus. It's not a solution for this one here because with that initial condition, because it never could meet. So again, that is not a solution for your differential equation. It would have been part of the graph of this function here. That's not what we're dealing with here. This solution that we wound up with here would only be valid from negative infinity to positive 1. Not counting positive 1 either, because it can't be positive 1. But the interval of solution would be negative infinity. Whoa, let me go back to a black or something else here so you can read it better. Your interval of solution would be negative infinity, this is ugly, less than x, less than, not less than or equal to, less than 1. That is an x there. Okay. That's your interval of solution. That's the only place where this differential equation with that initial condition has a valid solution. Anywhere along that curve. Everywhere else, no. Okay. Over here, no. This is not part of the solution for the differential equation. It would be part of the graph of your rational expression, not a difference of your differential equation. All right.
Professor?
Yes.
We have 3 minutes left.
Oh my goodness, how could that be? Okay. I guess we'll start next time on a fairly simple topic here. It's called attractors and repellers, so I don't think it'll take us very long to do. So we'll start the bottom of page 42 and move on from there. Okay? Let me make sure how in the world did I do this? I forgot to mark Ricky here when she showed up. Sorry, Ricky. I got you now,
We
though.
can't hear you.
All right. Billy was the only one absent today, right? I don't know where I was doing with my... For some reason, I marked... Okay, let me see. How many people...
I hear you.
Okay, we had 4 students here. What I did, for some reason, I marked Billy here when it was Ricky who came in. I don't know how I did that. So Billy was absent and Cole is absent. Sorry, I was facing slightly away from the thing. I'm just basically muttering to myself, and as my dad used to say, well, that must have been an intelligent conversation. But no, we're missing Billy and missing Cole. So now, homework exercise. That's what I meant to do. That's why I did. Oh, we almost finished 2.1.2. Just got a little bit more to do, but I think you can do any of the odd exercises, 1 through 1 or 3, either one of those answers in the back of the book. I think you could do any of the odds 5 through 11. Those answers are in the back, I think. If they're not in the back, don't mess with them. I think you can do 13. Its answer should be in the back. And you probably can do 15. I'll let you decide whether you want to do that or not. I think you can. Okay, then in 2.1.2, you can do number 19. Let me face the book. You can do 19 and any of the odds 21 to 27. And I think you can do 29. Okay? Yeah, you should be able to do 29. You don't have to mess with the rest of those if you don't want to. Now, here's another thing. Do you have to turn in to me some homework? No. I want the next thing you turn in to me to be your first test. Now, if you want to turn some homework in, if you're having trouble doing any of those exercises I just did, by all means, send those to me. Say, I can't get the answer they had in the back of the book. What am I doing wrong? I'll love to see those. It's not going to count against you. That counts for you because that helps you see where you may have been making a mistake or if the book made a mistake. So if you have any problem with the homework exercises, please send those to me. But if you're not having problems with them, you don't need to give me any more deliverables. The next deliverable I want from you is that first test. And that's not immediate. It's whenever you can get it done before we get to the end of chapter 2. Okay? Any questions?
No, sir.
All right. I think we just ran out of time. So have a good weekend. And of course, working on differential equations will guarantee it's a good weekend, right? Of course. Okay. So I'm going to end the recording. Take care. We'll see you Monday. Or Tuesday. Yeah, Tuesday.